All right, so even though due to bad officiating, among other reasons, Yale lost and is not in the NCAA tournament, we will still do an NCAA tournament. It is mandatory. You must participate in this class or you will fail. All right. I have tried to design a tournament so that you will not be embarrassed based on your lack of basketball skills or knowledge, nor will your skill sets help you in the tournament. Instead of doing mundane things such as, who wins, we're going to be guessing even or odd for the total sum of the score. Okay? So for each game, do you think it's going to be an even total score or an odd total score? Who do you think is going to win, even or odd? In some sense, you can completely ignore all the names. Now, if you want to pretend that maybe Kentucky has a tendency towards odd numbers and Hampton Manhattan has a tendency towards evens and use that to influence your decisions, by all means, go for it. But just fill this out with even, odd decisions, and then let me know in the end who wins even or odd, going all the way. And we'll see who does the best in the class, and there will be some prize. Okay? If you can find another pool that has less basketball knowledge, please let me know. I was trying to find the simplest one where no one will have a competitive advantage or disadvantage. All right, so what I want to do for today is I want to talk about differentiating identities. This is one of my favorite techniques. Yes?
So you want it for every round all the way through?
Yes, every way, all the way through. Every pick, do you think it's going to be even or odd for the score? Okay? There could be some slight advantage if you look at historical tendencies of scores in basketball games. Are you more likely to have an even or an odd total score? My gut feeling is that research is probably not going to be that helpful. All right? For people who want to do a real NCAA tournament, I'm actually working with the neighborhoods and the Williams Sports Analytics Group to actually have a real tournament, and I will send you information about that with prizes as well. All right. So I want to talk about differentiating identities, and I wanted to talk about it initially informally. Identities are the bread and butter of mathematics. They are very hard to prove. So what was the first identity we proved in this class? Anybody remember? Day one. It's an identity you should have seen before, but we re-derived this formula. What did we prove on day one? Hint, it's related to this, or at least the proof we gave was related to this. What formula did we derive on day one? The geometric series formula. There's the standard algebraic proof where you write, S as 1 plus r squared. Then you write rs as r plus r squared plus dot dot dot. You subtract, and you get 1 minus r times s after you factor is 1. Therefore, s equals 1 over 1 minus r. This is the algebraic proof. You might be worried that we're dealing with infinities, so if you're worried with infinities, we truncate at r to the n. We'd have r to the n plus r to the n plus 1. Now when we subtract, we would get the following, and we get minus r to the n plus 1 over 1 minus r. This is much better, and now we'd call all these Sn, and we could then take the limit as n goes to infinity of Sn will be 1 over 1 minus r. And if the absolute value of r is less than 1, everything is well defined. So this is the geometric series formula. Geometric series formula. It's one of the most important formulas in mathematics. When we were doing Calc 3, doing sequences in series, this was the key behind things like the comparison test, ratio test, root test. We use this all the time. It's an extremely useful formula. We had a better proof, it was a little bit more work, involving a memoryless process in bird and magic shooting. Once we do all this work, it's a shame to just throw it away and stop. What we would love to do is see, can we milk this for additional results? So again, every time you prove an identity, that's work. What we want to do is we want to generate new identities from old identities effortlessly. And what I'm going to show you is a way to generate infinitely many new identities from this identity. And the first 2 people in the class who master this will get a set of Ginsu knives. It sounds like I'm trying to sell you something. And I am. I'm skipping some very big technical steps. What class do you think I'm skipping? Real analysis. So over here, this initial argument when I didn't have the n, and I subtracted, and then I said, oh, look, s is equal to 1 over 1 minus r. That was completely skipping all the technical difficulties of dealing with infinite sums, worrying about convergence and whatnot. You can make arguments like this rigorous. In this case, this is a very nice way to do it by truncating. But to do the subject properly, you need to do a little bit of real analysis. What I want to do in the first class is, actually you can even hear Professor Gowdy, I think, and I don't care, he doesn't listen to these YouTube videos. A few classes down, you'll probably hear all the real analysis you need subconsciously throughout the semester as he's teaching. But rigorously, what you want to do is you want to use real analysis and show that you can deal with the infinite. That's the step I'm going to mostly skip today. So here's how differentiating works. So you start with the following formula. Let's say we have the sum, n goes from 0 to infinity, of x to the n is 1 over 1 minus x, or I'll write it as 1 minus x inverse. So we have a really nice formula here. What I want to do is I want to differentiate both sides with respect to x. So I take d by dx of both sides. Sum n goes from 0 to infinity of x to the n. And now the derivative on this side is no problem. D by dx of 1 minus x inverse. The negative 1 comes down, but I'm also going to get a negative 1 from here, so that will reinforce. And I'll get 1 minus x to the negative 2. Now, what would you love to do on the left-hand side? You'd love to interchange the derivative and the sum. I was supposed to remember to bring my cat in the hat because it has the Princeton colors to justify interchanging the sum and the derivative. I forgot that hat. The only hats I could find in my office today were my Williams math hat and my graduation hat. So I will actually put those on later today and actually justify the interchange rather than just hand waving. This is what happens when you forget to prepare properly. But for now, let's just interchange. And when we interchange, now we have d by dx of x to the n. And now what happens when we take the derivative? Well, that's just going to be the sum. N goes from 0 to infinity of n x to the n minus 1 is 1 over 1 minus x. This is very similar to some expressions we saw on the exam, where instead of x we had maybe p or q or something like that raised to a power. And now if I want to evaluate this, all I have to do is put in a specific value of x. There's one thing that looks a little bit annoying, though. I start off with the sum of x to the n, and now I have n x to the n minus 1. And so frequently, I might be giving you as an example, find the sum n goes from 0 to infinity of n over 2 to the n, which would be the sum n goes from 0 to infinity of n times 1/2 to the n. This is not quite what we have. It's really close. There are two ways around it. One way around it is I can say, well, look, I've got x to the n minus 1. I could just pull out an x. And if I pull out an x, then I'll have nx to the n. Everything looks fine. The other thing we could do is instead of taking d by dx of both sides, what could I take? Yes. I could take x times this. The d by dx is good in that it brings down the n, but it changes the power of x. If I use the operator x d by dx, then the advantage of that is now the power of x stays the same. It's just a question of which is the better way to do algebra. And so now I would have over here x d by dx. And now this is just set up a little bit better for doing the algebra. So again, depending on which expression you're looking at, sometimes it's better to use d by dx, sometimes it's better to use x d by dx. If you want to calculate things like the first moment, second moment, third moment, the x d by dx is really nice. If I want the second moment, I'm getting the sum of n times x to the n. If I want the second moment, I just apply it again. If I want the third moment, I apply it again. What's the potential drawback about using multiple copies of x d by dx rather than just d by dx for this problem? When it's making the left-hand side much nicer. What's the problem? Yes?
It makes the right-hand side.
Yeah, it makes the right-hand side. I mean, there's no such thing as a free lunch. right? If you're getting something in one place, you're almost surely losing in another, all right? So this is one of my favorite expressions. There ain't no such thing as a free lunch. If you make the left-hand side nicer, there's a cost. The cost is the right-hand side is worse. What do you have to use here? If I want to take the derivative of this again. Quotient rule or product rule. I'm lazy, I hate the quotient rule, so I mentally think of it as a product rule. Either way, though, you've made the derivative harder on the right-hand side. Usually, it's a worthwhile trade. So let's do an example. So let's do a geometric random variable. So we'll say x is geometric p if the probability x equals n is, let me see if I get this right. For n in 0, 1, 2, ... So I'm going to say x is a geometric random variable if the probability equals n is 1 minus p times p to the n. Is this a probability distribution? What two conditions do we have to check? Always positive. Well, be a little bit weaker than always positive. Non-negative. Right. So it's non-negative. And the other one? Integrates to 1, sums to 1. And in fact, that's probably why I put the 1 minus p there. So if I now sum over n of the probability x equals n, I'll get the sum, n goes from 0 to infinity, of 1 minus p times p to the n, 1 minus p, and then the sum of p to the n is just 1 over 1 minus p, so it's 1. So this is a random variable. Okay? And so the question is, where might we want something like this? We've actually seen something like this. There's a nice interpretation. So this is telling us the probability that x equals n is 1 minus p times p. A better way of writing this is, right, x is, I'll do it this way. Have probability of p of failure 1 minus p of success, toss this coin till get a success. So we're going to be tossing a coin until we get a success. And so what does that mean? If the first success is on the nth try, we have n minus 1 failures, and then we have a success. So in some sense here, I'm just interchanging what we would normally call p and 1 minus p. It doesn't really matter which one I call which, but you've just got to be careful when you're looking at this. This should also tell you what kind of coin we want to use. What kind of coin do we want to use? Fair. Why? Yes! So for fair coin, 1 minus p equals p. And it doesn't matter if we get things wrong. If we mix things up on a fair coin as to what's a success and what's a failure, we're going to be okay in our counting.
So this is the probability you get a success on the n plus 1 toss.
Oh, okay, yes. Yes, this would be the probability you get a success on the n plus 1 toss. Now, does it make sense that you could get a success on the 0th toss? No. So there's lots of different ways in terms of how you might want to rewrite this. And so here, I'm writing this down so my success is on the n plus 1 toss. You could rewrite it so that the success is on the nth toss, and then redefine it and not allow n to be 0. And so there's lots of different ways. This is a great point as to how you might want to rephrase this. And if I want to, I could write this so it's n minus 1, and now n goes from 1, 2, 3, etc. And that's absolutely fine. OK, so we now have a random variable. And now let's try to calculate what is the mean and what is the variance of this geometric random variable. So we have x is geometric p. All right, so we want to calculate the expected value of x. By definition, this is the sum, n goes from 0 to infinity of n probability x equals n. So this will be the sum, n goes from 0 to infinity of n times 1 minus p times p to the n. All right, I can pull out the 1 minus p, and I'll have the sum, n goes from 0 to infinity of n p to the n. We just figured out what that formula is. I'm going to just write this the long way and in a sense rederive what we have. It's x d by dx of the sum, n goes from 0 to infinity, of x to the n. And then when we're done, what do we evaluate x at? So what would we evaluate x at in this expression? So I want to get the sum, n goes from 0 to infinity of n p to the n. I take the sum of x to the n, which I know, take the derivative with respect to x, and then multiply by x. And then where do I evaluate this expression? I evaluate this at p. So if you already remember the formula, if you just recall that we have it over here, we could just plug in directly and say it's p over 1 minus p squared. Or if you don't remember that, if you want to go through the process, you could go through it like this. And I'm going to replace p's with x, I'll differentiate with respect to x, and then I'll specialize to the number I care about. And the reason is if you're doing a specific problem, they might tell you p equals 3/5. You can't take the derivative with respect to 3/5, right? You have to take the derivative with respect to a variable. So rather than taking the derivative with respect to p, because p is a fixed number, and in the particular problem you're looking at, p might be given, I'm going to just treat this as a variable. So I would have 1 minus p, and then x d by dx of 1 minus x inverse. Evaluate this at x equals p. I'll get 1 minus p times now x over 1 minus x squared at x equals p. So it becomes p over 1 minus p. So let's think about what happens as p gets larger. What happens to the expected value as p gets larger? Yes?
It gets higher.
It gets higher. So what we're saying here is that if we call this the geometric with probability p, this is telling us that the larger p is, the longer it's going to take us on average before we get our first success. That seems reasonable because p is here our probability of failure. The smaller p is, the closer p is to 0, the smaller the expected value is. This also might tell you that maybe this is not a good definition of a geometric random variable. Do you like this as the definition of the geometric random variable? Do you like p as the probability of failure? So what do you want? Yes?
We could just substitute in a new variable.
Okay. What new variable?
Q equals 1 minus p.
Q equals 1 minus p. But so, the question comes down to if x is geometric p, do we want 1, the probability x equals n, to be 1 minus p, p to the n, or do we want it to be the probability x equals n to be p 1 minus p to the n? Which would you rather have as the definition of a geometric random variable? Does the universe care which choice we make in this class? No, I do not have this kind of control over the universe. Are both choices defensible? Absolutely. What's nice about this as well, I'm raising something to a higher and higher power. Let me have the thing that I'm raising to power be my parameter p. But then the interpretation here is p is my probability of failure. This seems so negative and down, right? This is a much more uplifting view of probability, looking for success. So I'm deliberately not going to say which one is the standard definition. There is one that is standard, there is one that is not standard. Okay, so I will let you think as to which one, if you could choose, which one would you choose, and then you can see which one the literature has chosen. I will say sometimes the literature chooses poorly. So here's sine x, here's cosine of x. This is one of my favorite or least favorite examples. Which is cosecant? Where should cosecant go? It should go with cosine, but cosecant actually goes here, it's 1 over sine, and secant goes here as 1 over cosine. I think this is horrible notation, but this is the notation we use. All right, now that we've calculated the mean with this definition, we could calculate the variance. So there's several ways to calculate the variance. One is we could calculate variance as the expected value of x minus mu squared, or we could calculate it as the expected value of x squared minus the square of the expected value. I really like this formula. What's nice about this formula is we've already got the expected value of x done. Now we just need to calculate the expected value of x squared and then subtract. So what we would do is we would apply x d by dx again. And that would lead to the expected value of x squared. So we would get the expected value of x squared would be x d by dx acting on x d by dx of the sum, and it goes from 0 to infinity of x to the n. And when we do that, we will then get the beautiful expression of the sum of n squared. N goes from 0 to infinity of n squared x to the n. This is then the same as x d by dx acting on x d by dx of 1 minus x inverse. And then you'll just evaluate it at p. We've now reduced it to a calculus problem. So I'm going to stop here. I'm not going to do the algebra. You can now finish the job by just using calculus. It's not pleasant to have the x's here, right? Because we have the x's, we have to use the quotient rule. But everything is set up nicely over here. So again, most of your life as a theoretical mathematician is all about trying to do the algebra in the nicest way possible. This is why I want to spend the time talking about how to approach the algebra rather than doing the brute force calculations. This is a 300 level math class. You've survived to this point. You can do the calculus like this. I want to talk to you about how I view calculations like this and how I'd like to try to arrange things. So here I see a quotient rule, which is not necessarily pleasant, but it's not horrible. And of course, what could you use to calculate this derivative? What could you use to calculate the derivative? A computer. Mathematica loves stuff like this. To calculate the first one, it would just be, derivative of, 1 minus x to the negative 1 with respect to x. Multiply by x, take the derivative again with respect to x. And something like that, and that should be the command for Mathematica to quickly calculate the derivative for you. All right, so let me talk about how else you could do this problem. So the other way to do this problem is not to use x d by dx. So let's make things nice on the right. So we'll apply d by dx twice. So now we get d by dx acting on d by dx of the sum, and goes from 0 to infinity of x to the n, equals d by dx of 1 minus x inverse. All right, the right-hand side is not a problem. I take one derivative, I get negative 1, 1 minus x to the negative 2. With a negative 1, it reinforces. It's a 1 minus x to the negative 2. I take the derivative. If I've done it correctly, I should get 2, 1 minus x to the negative 3. On this side, what I will get is, assuming I can pass everything inside, is n goes from 0 to infinity of n minus 1, x to the n minus 2. So this is unfortunately not the second moment. I've got n squared times n. Also, what else is wrong?
N minus 2.
I've got the n minus 2. The n minus 2 is the easiest way to fix. How can I fix the n minus 2? I could change the bounds in some. There's something easier to fix the n minus 2, though. Multiply by x squared. So if I multiply by x squared, I get the sum, n goes from 0 to infinity of n squared minus n, x to the n equals x squared, 2x squared, over 1 minus x cubed. This is almost the second moment. Bless you. So this is the expected value of x squared. That's the sum of n squared x to the n. What's the sum of n x to the n? What would that sum equal? Mean. So that would be equals 2x squared over 1 minus x cubed. Well, I'm trying to calculate the expected value of x squared. Instead of getting the expected value of x squared on the left, I get the expected value of x squared minus the expected value of x. Not a big deal. Move this over to the other side. And there's a formula for the expected value of x squared. So you have to decide which algebra is better for you. For this problem, I might actually do the algebra like this. And instead of calculating the second moment directly, instead of getting the expected value of x squared directly, I get a polynomial involving the expected value of x squared and the expected value of x. I get a nice relationship between the two of them, and then I solve for the second moment. Then I take this and then I subtract off the expected value of x squared. And I'll choose x to be whatever p was. So again, it's all about how you want to arrange the algebra. Okay, so there's a lot of good stuff here on this problem. Any other questions on this geometric random variable? So again, either way is fine. There's going to be a lot of calculations like this throughout the semester where you can do it multiple ways. It's just a question of which way you prefer. All right, the next is the exponential random variable. And just like the geometric random variable, it turns out there's two different definitions. So exponential. So we can say x is exponential lambda if the density function of x is equal to 1 over lambda e to the negative x over lambda, or the density function of x is lambda e to the negative x lambda. So in order to try to maybe minimize confusion, I'll say y is, and I'll write it in script, exponential, and I'll use a new parameter. I'll use omega. So I'll call this y. So here's a y, and here's omega. So this should be a pretty straight conversion factor between the two of them. What do you think the conversion factor is between the two of them? What's the interpretation? How do I get from one to the other? Yeah, so basically lambda equals 1 over omega. This is how you pass from the two. Both of these are called the exponential distribution. Unlike the geometric here, I will put my foot down and I will say which one I prefer. If I tell you I have an exponential random variable with parameter lambda, do you want the mean to be lambda, or do you want the mean to be 1 over lambda? Yeah, I'd rather have the mean be lambda. And so for this one, we actually get the mean as lambda. For this one, we get the mean as 1 over omega. If you look at this, we're measuring x in units of lambda. And so to me, this is the more natural way to define things. So for both of these, you have to check to see that they're non-negative. You have to check and see that they integrate to 1. I'm not going to bother doing those calculations. All right, how would we calculate the mean? So the expected value of x is just the integral from 0 to infinity of x 1 over lambda e to the negative x over lambda dx. How do we do this integral? How do we evaluate this integral? It's been a while, I know, since we've done calculus. Integration by parts. Integration by parts. If anybody does not like integration by parts, I'm happy to replace integration by parts with problems involving partial fractions. I'm happy to have no partial fractions for the most part in this course. I do expect us to be able to do integration by parts, use substitution. These are extremely important. If we want to calculate the second moment, if we want to calculate the variance, we'd have x squared. We would have even more integration by parts. All right. If I don't have the x, if I just want to calculate this integral, it's not so bad. Okay? So this is just proving that it integrates to 1. So I'm going to assume that we've done our basic calculus, and we know the integral from 0 to infinity of 1 over lambda e to the negative x over lambda dx equals 1. If you want, do u substitution. Let u equal x over lambda, du is 1 over lambda dx. So I will assume we start off with this expression. What I want to do now is I want to show you how you can use differentiating identities to bypass integration by parts. All right? So again, I do not think integration by parts is that bad, in the relative scheme of what I can throw at you in terms of calculus. But there's no need to even do integration by parts. But again, if we're going to be differentiating an identity, what do we need to start with? If you're going to differentiate an identity, you need to start off with an identity. The identity we have is this expression. I'm going to move lambda over to the other side. So we're going to start with the following. The integral from 0 to infinity of e to the negative x over lambda dx equals lambda. I could keep lambda on the other side. If I keep lambda on the other side and I differentiate with respect to lambda, I'm going to have to use the product rule. I can make my life a lot easier by putting the lambda over on this side. What should I apply to both sides? What operator should I apply to both sides? There's two possibilities, two natural guesses. Can I differentiate with respect to x? Why can't I differentiate with respect to x? X is a dummy variable. We've integrated x out. There is no x on the right-hand side. If you want, I'll get in trouble with my colleagues. I could replace it with a smiley face. Okay? E to the negative smiley face over lambda d smiley face. Although based on how people are looking today, maybe I should not use a smiley face. I'll use a sad face. And try to do an integral like that. Would you ever differentiate with respect to a smiley face or a frowny face? No. Right? You've integrated it out. It's gone. No more smiling in this class. All right? We can't differentiate with respect to x. It's a dummy variable. It's gone. What's the only variable left that we can differentiate with respect to? Lambda. Now, if we differentiate with respect to lambda, we have an x over lambda. When this comes down, we're going to get a negative x over lambda squared. We're going to get an x over lambda squared. So it's going to turn out that I'll leave it as that. We'll apply d by d lambda to both sides. And so now we'll assume we can move it inside. When we apply d by d lambda, e to the negative x over lambda dx, the derivative of lambda is just 1. Now we get integral from 0 to infinity of x over lambda squared, e to the negative x over lambda dx equals 1. Now what should I do? What should I do to finish the problem? This is damn close to what we want for the mean.
Just multiply by lambda.
Multiply by lambda. View this as the integral from 0 to infinity of x. We need to keep a lambda in the denominator because that's the density. And when we multiply through by lambda, here's our mean. And there's the expected value of x. We've completely bypassed integrating by parts. You can do this now if you want to get the second moment. If I want to get the second moment, I would have to take the derivative with lambda twice. Well, what I would probably do is I would stop at this point. And if I wanted the second moment, what I would probably do is I would start now with the integral from 0 to infinity of x squared over lambda, x over lambda squared, e to the negative x over lambda dx equals 1 is the same as the integral from 0 to infinity of x e to the negative x over lambda dx equals lambda squared. And then I would differentiate both sides with respect to lambda and then multiply through by 1 lambda. Or maybe better, apply lambda d by d lambda. So it takes a while to become really comfortable and fluent in the best ways of doing the algebra. Okay? But if you spend a little time, if you try to think, what do I want to get? Well, I want to get the mean. If I want to get the mean, well, let's look at the density. The density is 1 over lambda e to the negative x over lambda. This is my density function. To get the mean, I need to multiply this by an x. So now I want to take this and I want to write this as somehow x times the density. And this is what's suggesting I need to multiply through by lambda. I need to pull a lambda over to the other side. When you look at this the first time, it's not at all clear. Should I take the derivative with respect to lambda, lambda d by d lambda? It's not clear. Do it once and see what's going on. And then over here, in terms of now continuing, I don't want to keep differentiating this. This would be a product rule. I could do it, but it's painful. It's more work. Why not pull the lambda over to the other side? And now I have a really nice function with respect to lambda on the right that I can differentiate. And now I can just keep getting the moments without too much trouble. OK. Any questions on the exponential? OK. So what I want to do now is I'm going to hold off on doing the Poisson. If there's time, which I probably don't think there will be, we'll do the Poisson. But if not, I want to jump to and just give you a sense of why this is true. So to prove why this is true in general requires real analysis. But there is one special case where we can prove it without having to resort to the fancy hats. I don't get to wear my hat that often. I will wear my hat. All right. So it is not true because I am wearing a hat because I have a PhD in mathematics. All right. What is the simplest infinite series can you think of that we can work with? What infinite series do you think is going to be the nicest one to work with? Yes? Geometric. Why is the geometric so nice? So we start off with the sum, n goes from 0 to infinity of x to the n. It's 1 plus x squared plus x to the n plus a sum, n goes from n plus 1 to infinity of x to the n. And here is the secret that makes the geometric series so nice. Actually, let's do the algebra. Let's have it go up to x to the n minus 1 here, and we'll go from x to the n onward. What can you tell me about this over here? What is this? It's a geometric series. What we have is 1 plus x to the n minus 1, plus we'll pull out an x to the n, and then we'll have a sum, n goes from 0 to infinity of x to the n. Well, what does that sum equal? It equals just 1 over 1 minus x. 1 plus x squared plus x to the n minus 1 plus x to the n over 1 minus x. It's a finite sum. This is the only series I know where we are this fortunate. All right, what's really working to our advantage here, and at this point I no longer even need the hat. What's working to our advantage is this tail has the same shape as the initial function. If you want to be really fancy, you can even do the bring it over method, and now bring this over to the other side and get 1 minus x to the n over 1 minus x equals this sum. Bring that over. I'm not going to be that fancy. We can leave it like this. It's a finite sum. We can differentiate term by term. And so now the derivative of the infinite sum would now be the derivative of this, which would be the sum. I'll use m, I guess, a new variable. M goes from 0 to n minus 1 of m x to the m minus 1. Now we have the derivative of this piece. Oh, actually, I could use the letter n. I'm no longer using n on the other side. Now, how do I take the derivative of this? What do I use? So how do I take the derivative of x to the n over 1 minus x? Yeah. So at this point, I've got to use the quotient rule. All right. It's been a long time since I've done Calc 1, so check me. It's n x to the n minus 1 times 1 minus x to the n. The derivative of 1 minus x is negative 1, so that becomes a plus, I think, divided by 1 minus x squared. And now we take the limit as n goes to infinity, and the absolute value of x strictly less than 1. Well, since the absolute value of x is less than 1, the denominator is fine. X to the n goes to 0. And then while n goes to infinity, we have n times x to the n. This is growing exponentially. I'm sorry, this is decaying exponentially because x is less than 1. This is growing only polynomially. So n x to the n is going to go to 0. So you can see in the limit as n goes to infinity, it's going to converge to the sum we specified. So in the case of the geometric series, we can actually make the argument precise. In general, the way you would make this argument precise is you would take the sum, and then you would say, well, you know what? I believe that the derivative of the sum is the sum of the derivatives. I'm going to look at the difference term by term and show that that goes to 0 and do some bounding. If anybody is interested, I'm happy to provide additional details as to how you would do this. You would go back to the definition of the derivative, and you would show that the two sequences are close. Okay? I actually did lecture on this in my advanced analysis class in the fall. So if anybody does want to know, let me know, and I can show you exactly where that would be the case. But we are lucky here, and this is the only example I know of where we're this lucky, that we can bypass all of this because we know that the sum of the tail is just another copy of a geometric series. All right, so we've still got about 4 minutes left, so we can do a Poisson random variable. So we'll say x is Poisson with parameter lambda if the probability that x equals lambda is equal to e to the minus lambda, lambda to the n over n factorial, n is 0, 1, 2, dot, 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 and 0 otherwise. So this is going to be a Poisson random variable. It's non-negative, clear, as long as lambda is non-zero. So we'll say lambda is greater than 0. And then the fact that it sums to 1 comes from the sum of lambda to the n over n factorial, and it goes from 0 to infinity, equals e to the lambda. This gives us the sum is 1. OK, so now we have a Poisson random variable. We want to calculate its mean. We want to calculate the expected value of x, which is going to be the sum. N goes from 0 to infinity of n e to the minus lambda, lambda to the n over n factorial. Well, when you look at this expression, one part of this expression isn't that bad. Which part of the expression isn't bad? So which part doesn't really bother us? In looking at this infinite sum, which is the non-troublemaker? E to the minus lambda. Everything else involves n. I can pull out the e to the minus lambda. That's not bad. The difficulty is how do we handle the rest? Well, we've got to start off with an identity. What's the only identity we know? This is the identity. It's essentially very similar to what we did with the exponential random variable. We moved the lambda to the other side. We moved the normalization constant to the other side. So if you want to do like a grand unified theory of this lecture, it's moving the normalization constant over to get an identity. So by moving that, we're in great shape. So move normalization constant over. So now we get the sum, n goes from 0 to infinity, of lambda to the n over n factorial equals e to the lambda. So what should we apply? In the interest of time, I'm going to apply lambda d by d lambda because I'm learning, it's been like 3 examples already. I know that if I apply a lambda, I keep things to the right degree. I'll now get a sum, n goes from 0 to infinity, of n lambda to the n over n factorial. And what's the derivative of e to the lambda? E to the lambda. But I'm applying lambda d by d lambda, so I get lambda e to the lambda. I now pull the e to the lambda back to the other side because I want my probability density. So I'll have n times e to the minus lambda, lambda to the n over n factorial equals lambda. So the mean value of a Poisson random variable with process lambda is just lambda. If you want to calculate the variance, it calculates similarly. All right, so I'm going to stop here. I strongly urge you to try to calculate the variance, the second moment, the third moment, general moments of this. It's a great way to see the power of differentiating identities. But notice how we are not integrating by parts. We are not evaluating difficult sums, so long as we know something. So the idea is I don't want to do anything new in this class. I want to just, milk all the math you've learned up till now.